Lol, last time I promised that the next video is gonna be problems of subscribers, and it ended up taking a few days for me to solve anything that's remarkably interesting. So if I solve any more problems, I will make a day about them, but you guys are geniuses. I don't know how you solve that. But here's one that I could solve. Integral of this product. So my idea here initially was to try to do it recursively, but didn't bring me anywhere. What I ended up doing is using partial fractions for this. So let's rewrite this with my own pen. We have this product k equals 0, 1 over x plus k dx. Now, if we were to look at the first few ends, then you can observe that all of that is just sum of different logarithms after you do partial fractions. So what we're gonna do is we're gonna try to generalize that. First, let's generalize partial fractioning. Say we have alpha over x plus b times x plus c. Let's generalize partial fractions. What we know about it. Okay, first of all, let's write it down. Big A over x plus b plus big B over x plus c. Now let's actually find those. So for one, we know that a and b are opposite because otherwise the x's wouldn't cancel out. So a equals negative b. And the other thing we know is that a capital times c plus b capital times b is equal to alpha. Now let's use the substitution that we know of. A times c minus b. Okay, minus a b is equal to alpha. Now big A is going to be alpha over c minus b. So we have acquired that. Now we're to observe this entire thing. It's evident that we can go ahead and multiply out some very specific element by others. And in the result, if we were to disregard other stuff, again, let me just write down this result here. Alpha over c minus b. Here we have 1 over x plus b. Minus 1 over x plus c. What we have here is essentially that if we were to multiply one fraction of this type over another fraction of this type, then they retain the denominator of x plus b. They just gain multiplication by a coefficient. So it's pretty evident that we can just multiply out one element by others, disregard other parts of the product and leave this one out, this one per se, and then say that what we got is the final part of the product for this one, x plus 2. So what we can do is we can just multiply it out for others, ignore the second part, and only consider this coefficient. So suppose we define a function for doing precisely that. Say f of 0 is just 1 over x plus k, and f of I is f of I minus 1. Now, to get the previous coefficient that we had, aka alpha, what we do is we multiply this by x plus k. Next, now that we have alpha, we have to divide it by c minus b. I'm not gonna do this formally and define a bunch of other arguments. So c here we don't know c. Let's leave it like that. And k we know it. B here is just k here. So now what we have left is times 1 over x plus k. Notice how this and this cancel out. So what we have left is f of I minus 1 times 1 over c minus k is essentially what we have done is we have recursively defined the coefficient for every part of well, this product after we expand it out into fractions. So that's nice because now we can say that a of I is going to be a product. Well, now we just have to go through every c that is present here, which is going to be every element from 0 to n except for k. So now we know that the coefficient is going to be 1 over x plus k times the product I equals 0 up to k minus 1 of 1 over I minus k times the same product but from I equals k plus 1 up to n of 1 over I minus k. Now this over here is going to be just 1 over n minus k factorial. This over here is practically just negative 1 to the power of k. Okay, and this is going to be just k factorial. It's evident from this part. So just writing like this, minus 1, minus 2, up to minus k. And well, the negative sign comes from the fact that we're multiplying negative numbers, and k here is, so if it's even, then it works appropriately. So essentially the coefficient is going to be just this product. So we have the integral of sum from k equals 0 to n negative 1 to the power of k times k factorial n minus k factorial of x plus k dx, and we can finally integrate it. This gives me the sum of a bunch of logarithms. We're integrating from after integrating we have a sum from k equals 0 to n. Have a minus 1 the power of k times natural logarithm of okay, no, with absolute sign. I mean, technically I could define it like piecewise, but that's going to be taking too much time. I want to deal with that. K factorial and minus k factorial. That's it for today. Hope you liked the video. Bye.